Welcome to this session on methods in biostatistics. Today, we are going to explore one of the most fundamental decisions every researcher must make, choosing between primary and secondary data. Whether you are tracking a new viral outbreak or studying decades of ecological changes, the type of data you choose will dictate your budget, your timeline, and the ultimate success of your research. Let us dive in and understand how these two approaches shape the world of biological sciences. Before we look at formal definitions, let us start with a simple analogy. Imagine you are trying to bake a very special, custom-flavored cake for a friend's birthday. You have two choices for getting your ingredients. You could go directly to a local farm, milk the cows yourself, and gather fresh eggs with your own hands. Alternatively, you could simply drive to the local supermarket and buy milk and eggs that someone else has already collected and processed for you. In the world of biostatistics, gathering data works exactly the same way. Going to the farm is like collecting primary data, while going to the supermarket is like using secondary data. Now that we have our analogy, let us define what this means scientifically. Primary data refers to the original, first-hand information that a researcher collects directly from the source for a specific current research objective. Think of a scientist conducting a brand new clinical trial and measuring the blood pressure of 50 patients. They are generating primary data because those specific measurements did not exist before that exact moment. Because you are collecting it yourself, primary data gives you absolute control over the quality and relevance of the information, ensuring it perfectly matches your unique scientific question. In contrast to gathering everything yourself, let us look at the alternative. Secondary data refers to information that has already been collected, processed, and published by someone else, usually for a completely different purpose in the past. If our same scientist decides to look up historical blood pressure records from a hospital's database from 10 years ago, they are utilizing secondary data. The fundamental difference here lies in the origin and ownership of the data collection process. When you use secondary data, you are relying on someone else's work, which means you have less control over how the information was originally gathered. Understanding these definitions leads us to why this distinction is absolutely crucial for your research. The type of data you choose dictates the budget, timeline, and accuracy of any biological project. Primary data is incredibly important when you need highly specific, up-to-date information, like testing a newly developed vaccine. However, collecting this data is notoriously expensive, labor-intensive, and time-consuming. On the other hand, secondary data becomes a lifesaver when researchers have limited funding. It is also the only way to analyze massive historical trends, like tracking the spread of a disease over the last century, which would be physically impossible to collect firsthand today. To truly understand the practical difference between these two approaches, we can look at the mathematical model for the total cost of a research study. This simple algebraic equation helps biostatisticians justify their research budgets. The formula is T equals F plus the product of C and N. Here, T represents the total cost of the data collection process in dollars. F stands for the fixed costs, which are the initial expenses required just to start the study, like buying software or renting lab space. The variable C represents the cost per single observation, such as the price of one blood test. Finally, N represents the total sample size. If C is high, as in primary data, the total cost T increases rapidly as your sample size N grows. Now that we have our cost formula, let us apply it to a real-world scenario involving primary data. A biostatistician wants to study cholesterol levels by setting up a new clinic. We are given a fixed setup cost of $5,000. The variable cost for each individual blood test is $50, and the researcher needs a sample size of 200 patients. We start by writing down our formula. T equals F plus C times N. We substitute 5,000 for F, 50 for C, and 200 for N. Multiplying 50 by 200 gives us a variable cost of $10,000. Adding this to our fixed cost, we find that the total financial burden to collect this fresh, first-hand data is $15,000. This shows how quickly costs escalate when doing the groundwork yourself. Having seen the high cost of primary data, let us see what happens when a researcher uses secondary data for the exact same study. Instead of a clinic, the researcher purchases access to a national health database for a fixed license fee of $2,000. Because the data is already digitized, the cost per individual record is $0. The sample size remains 200 patients. Using our same formula, we substitute 2,000 for F, 0 for C, and 200 for N. Multiplying 0 by 200 results in 0 additional variable costs. Adding this to the fixed fee, the total cost remains exactly $2,000. This perfectly highlights the massive economic advantage of secondary research. Scaling up your subject count does not drain your budget. With both calculations complete, let us directly compare the financial impact of these two methods. We found that the primary data collection required $15,000, while the secondary data approach only cost $2,000. By subtracting the secondary cost from the primary cost, we can calculate the exact savings. $15,000 minus $2,000 gives us an incredible $13,000 saved. This proves that while secondary data might not be perfectly customized to the researcher's exact needs, it is vastly more economical. It is a perfect choice for large-scale biostatistical analysis when you are operating on a tight budget. To solidify our understanding, let us look at this visual flowchart comparing the two pathways. On the left side, you see the primary data process. The researcher interacts directly with the population of patients. The arrow connecting them represents direct collection, which, as we just calculated, involves high costs and high time investment. On the right side, we see the secondary data process. Here, the researcher does not interact with patients directly. Instead, the arrow points to a computer server or database, representing indirect collection. This pathway is characterized by low cost and low time investment. This diagram perfectly summarizes the structural difference between gathering fresh information and utilizing pre-existing records. Now that we have explored the pathways and the costs, we must recognize that choosing between primary and secondary data is one of the most foundational decisions a biostatistician must make before beginning an experiment. There is no single correct answer for every study. Primary data offers unparalleled accuracy and relevance because you collect it yourself, but it demands heavy investments. Secondary data provides a fast, cost-effective alternative, though it may lack the specific details your unique study requires. Ultimately, a great researcher knows how to balance their budget, their timeline, and their scientific needs to choose the right type of data for their specific project. As we wrap up this topic, let us review the key takeaways. First, remember that primary data is collected firsthand for a specific current purpose, giving you maximum control. Second, secondary data utilizes pre-existing records, saving you time and effort. Third, we learned that the total cost of any study depends heavily on fixed setup fees and the variable costs per patient. Finally, because the variable cost of secondary data is often zero, it remains highly economical, even for massive sample sizes. You now have a solid understanding of how to evaluate data sources for your future biostatistical research. Great job!